You must have watched the Avatar movie, and if you haven't seen it, that's completely fine, because today I'm going to tell you everything you need to know about this cinematic masterpiece and the fascinating scientific questions it raises. In the Avatar movie, there was a planet shown called Pandora, and this planet was so incredibly, breathtakingly beautiful that the entire world went absolutely crazy after seeing it. The visual spectacle was unlike anything cinema had ever produced before. There were glowing forests that emitted brilliant blue light at night, creating an ethereal landscape that seemed more like a dream than reality. There were floating mountains suspended impossibly in the sky without any visible support whatsoever, defying everything we know about physics and geology. Living on this extraordinary planet were aliens called the Na'vi, and these aliens were blue in color and stood an imposing 10 feet tall, making them significantly larger than any human. The most interesting and scientifically intriguing thing about them was that they could connect with trees and animals using their neural cues, the braided appendages that extended from the back of their heads. It was like a biological USB connection, similar to how we connect our phones to Wi-Fi networks, except this was a direct neural interface, allowing complete communication and even memory sharing with other living organisms. Asterisk, when I first watched this movie in the theater, completely immersed in its three-dimensional world, a profound question arose in my mind that has stayed with me ever since. Could there really be a place like this somewhere in our vast universe where such exotic and wonderful life could exist? Are there really aliens living somewhere out there in the cosmos that we don't know about, perhaps looking up at their own night sky and wondering the same thing about us? These questions have puzzled humanity for centuries, but only in recent decades have we developed the scientific tools and understanding to begin seriously investigating them. In today's discussion, we're going to try to answer these profound questions, and I'll tell you what scientists have discovered through decades of research, what theories they've developed, and whether a place like Pandora could actually exist somewhere in our universe, perhaps orbiting a distant star that we can see twinkling in our night sky. Asterisk first, let's understand in detail what Pandora actually was and where it was located within the context of the Avatar universe. In the movie, Pandora was not actually a planet at all, but rather a moon, specifically a habitable moon, orbiting a much larger gas giant planet. This moon was orbiting a massive planet called Polyphemus, a gas giant that would have been several times the size of Jupiter, our solar system's largest planet. The entire system, including Polyphemus and all its moons, was revolving around a star named Alpha Centauri. And this is where the science fiction begins to merge with science fact in a fascinating way. The most interesting thing, the detail that makes this all suddenly very real, is that Alpha Centauri is not a fictional creation at all. It's a real star system that actually exists in our galaxy, and it's the closest star system to our own solar system, our nearest stellar neighbor in the vast ocean of space. It's located only 4.37 light-years away from us, which in cosmic terms is practically next door, though the reality of that distance is almost incomprehensible to the human mind. Asterisk now, you might ask, what does 4.37 light-years actually mean in practical terms? How far is that really? Let me explain this in simple terms that will help you grasp the absolutely mind-boggling distances we're discussing. Light, the fastest thing in the universe as far as we know, travels at approximately 300,000 kilometers per second. To put that in perspective, that's about 186,000 miles every single second. This speed is so unimaginably fast that if light were racing around Earth's equator, it would complete 7 full rotations around our entire planet in just 1 second. Think about that for a moment. In the time it takes you to say 1 Mississippi, light could circle the Earth 7 times. Now, a light year, which is the unit we use to measure these vast cosmic distances, means the total distance that light travels in 1 full year, traveling at this incredible speed every single second of every single day. That distance works out to be approximately 9.5 trillion kilometers, or about 6 trillion miles. So when we say Alpha Centauri, our closest stellar neighbor, is 4.37 light-years away, what we're really saying is that it's approximately 40 trillion kilometers away from us, a distance so vast that the human mind really cannot fully comprehend it. Asterisk, to put this in even more practical terms that might help you understand the challenge of interstellar travel. If we were to travel to Alpha Centauri using our fastest spacecraft currently in existence, the Parker Solar Probe, which can reach speeds of over 430,000 miles per hour, it would still take us approximately 70,000 years to reach it. That's longer than all of recorded human history. Generations upon generations would be born, live their entire lives, and die aboard the spacecraft before it ever reached its destination. Hearing this, you might think that sounds impossibly, discouragingly far away, and you'd be right from a human perspective. But here's the thing that's truly mind-blowing. In terms of the universe's scale, this distance is absolutely nothing, barely worth mentioning. The universe is so incomprehensibly vast that you cannot even begin to imagine its true scale, no matter how hard you try. Our galaxy, the Milky Way, is about 100,000 light-years across. That means light, traveling at its incredible speed, would take 100,000 years to cross from one side of our galaxy to the other. And our galaxy is just one of hundreds of billions of galaxies in the observable universe, each containing hundreds of billions of stars. The distances between galaxies are even more staggering. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. The light we see from Andromeda today actually left that galaxy 2.5 million years ago, when our human ancestors were just beginning to use stone tools. Looking deeper into space, we can see galaxies that are billions of light-years away, meaning we're seeing them as they were billions of years ago, perhaps before our Earth even existed. Some of the most distant galaxies we've detected are so far away that their light has been traveling toward us for over 13 billion years, nearly as old as the universe itself. This is why understanding cosmic distances is so crucial when we talk about finding life elsewhere in the universe. The sheer scale of space means that even if alien civilizations exist, and statistical probability suggests they probably do, they might be so far away that we'll never be able to communicate with them, or visit them with any technology we can currently imagine. Now let's talk about whether there could really be a moon like Pandora in the Alpha Centauri system or anywhere else in the universe. Scientists made a huge groundbreaking discovery in 2016 that brought us one step closer to answering this question. They found that the Alpha Centauri system actually contains a planet, a real exoplanet orbiting a real star in that system, which they named Proxima Centauri b. And this discovery sent ripples of excitement through the scientific community. This planet is roughly the same size as Earth, what we call an Earth-sized world, with a mass estimated to be about 1.3 times that of our home planet. The most exciting and interesting thing about this discovery is that this planet appears to be at exactly the right distance from its star, positioned in what scientists call the sweet spot for life. This means conditions that are neither too hot nor too cold, with temperatures that could potentially allow for liquid water to exist on its surface. Scientists call this orbital region the habitable zone, or sometimes the Goldilocks zone, meaning it's that special place where conditions are just right, not too hot and not too cold, where life as we know it could potentially exist and thrive. To understand the habitable zone concept better, let me give you a simple example that will make this clear. Imagine you have a heater in your house on a cold winter day. If you sit too close to the heater, you'll feel uncomfortably hot, perhaps even burning hot, and you'll need to move away. If you sit too far away from the heater, you'll feel too cold and won't get any benefit from it at all. But there's a sweet spot, a perfect distance somewhere in the middle, where you feel perfectly comfortable, where the warmth is just right. Similarly, around every star in the universe, there's a zone, an orbital region, where conditions are neither too hot nor too cold for liquid water to exist. If a planet exists in this zone and has the right atmospheric conditions, water can exist there in liquid form rather than being permanently frozen as ice or boiled away as vapor. And this is absolutely crucial because where there's liquid water, life, as we understand it, becomes possible. The habitable zone isn't a fixed distance that's the same for every star. It varies dramatically depending on the type and size of the star at the center of the system. A larger, hotter star like a blue giant will have its habitable zone much farther out from the star, perhaps hundreds of millions of miles away, while a smaller, cooler star like a red dwarf will have its habitable zone much closer in, perhaps only a few million miles from the star. Our Sun is classified as what we call a G-type main sequence star, or a yellow dwarf star, a fairly average star in terms of size and temperature. Earth sits comfortably in the Sun's habitable zone at about 93 million miles away. The distance we call 1 astronomical unit. Venus, our sister planet, is too close at about 67 million miles from the Sun and became a hellish greenhouse world with surface temperatures hot enough to melt lead. Mars, the red planet, is too far at about 142 million miles and lost most of its atmosphere billions of years ago, turning into a frozen desert where any water that remains is locked up as ice. But the habitable zone is just the starting point, just the first box to check off. A planet also needs many other conditions to be right for life to emerge and thrive over billions of years. A planet in the habitable zone also needs to have the right mass to hold on to an atmosphere. It needs to have the right chemical composition with the building blocks for life. It probably needs plate tectonics or some similar process to recycle nutrients and regulate the climate over geological timescale. It benefits enormously from having a magnetic field to protect it from harmful radiation from its star and from cosmic rays, and it needs to maintain these conditions for long enough for life to evolve, which on Earth took billions of years. Even with all these factors in place, there's no guarantee that life will emerge. We still don't fully understand how life first began on Earth. And it's possible that the origin of life is an extremely rare event that requires very special circumstances. This is why finding even simple microbial life on another world would be one of the most important discoveries in the history of science, because it would tell us that life isn't unique to Earth, that it can arise wherever conditions are right. Now, let's discuss a planet that scientists have called Earth's big brother, and its name is Kepler 452b. This planet was discovered in 2015 using the Kepler Space Telescope, a remarkable instrument that spent years staring at a small patch of sky, watching for the tiny dips in starlight that occur when a planet passes in front of its star. When scientists first observed this planet and analyzed its properties, they were absolutely shocked and excited because this planet was so remarkably similar to Earth, in so many ways that they immediately thought life might actually be possible there. Kepler 452b is located approximately 1,400 light-years away from us in the constellation Cygnus, which means it's far beyond anything we could reach with current technology, but close enough that we can study it with our telescopes. This planet completes one orbit around its star in 385 days, which is remarkably close to Earth's 365-day year. This similar orbital period immediately suggests that it might receive a similar amount of energy from its star as Earth receives from the Sun. Asterisk. The most interesting and exciting thing is that Kepler 452b star is also very similar to our Sun. It's what we call a G-type star, just like our Sun, though it's actually slightly larger and about 20% brighter. The star is about 6 billion years old, which is about 1.5 billion years older than our Sun, which means it's had even more time for life to potentially develop on any planets orbiting it. This means that if you were somehow standing on the surface of Kepler 452b and looked up at the sky, you would see a sun very much like ours shining down on you, perhaps slightly brighter and slightly more yellow. The day and night cycle there would be almost the same as on Earth, with similar seasons. If the planet has a similar axial tilt to Earth's 23.5 degrees, you might see sunrises and sunsets that would look hauntingly familiar, with colors and patterns similar to what we see on Earth, though perhaps with subtle differences depending on the composition of the atmosphere. Asterisk. However, there's one major difference that would make life on Kepler 452 to be very different from life on Earth, and that's the planet's size and gravity. Kepler 452b is about 60% larger in diameter than Earth, which means it has significantly more mass and volume. Scientists estimate that if it has a similar composition to Earth, it probably has about 5 times Earth's mass. This increased mass translates directly to increased surface gravity. The gravity on Kepler 452b is estimated to be approximately double that of Earth's gravity. This means if you normally weigh 50 kilograms, or about 110 pounds on Earth, you would feel like you weigh 100 kilograms, or 220 pounds on Kepler 452b. Walking there would be very difficult and exhausting, like carrying another person on your back everywhere you go. Your muscles would have to work twice as hard just to move around, and if you tried to jump, you'd only get half as high as you could on Earth. Your heart would have to work much harder to pump blood through your body against the increased gravity, and over time, this would put tremendous strain on your cardiovascular system. Asterisk. If humans were to somehow colonize such a high-gravity planet, and that's an enormous if given the distances involved, we would need to undergo significant physical training and conditioning before even attempting to live there, or develop special exoskeleton suits or other assistive technology to help us move normally and prevent our bodies from being crushed over time by the relentless pull of gravity. Children born on such a world would develop differently from Earth children, with stronger bones and muscles adapted to the higher gravity. But they might also face health challenges we can't fully predict. Interestingly, if life evolved naturally on Kepler 452b, those organisms would likely be shorter and more compact than similar organisms on Earth, built low to the ground with powerful muscles and robust skeletal structures to handle the increased gravitational stress. Trees might grow wider rather than taller, and any flying creatures would need to be extremely powerful to overcome the stronger gravitational pull. Asterisk. The question that naturally arises is, could there actually be life on Kepler 452b? Scientists say that this planet is definitely in the habitable zone of its star, and that liquid water could potentially exist there on the surface, which is the first and most important requirement for life as we know it. The planet receives only slightly more energy from its star than Earth receives from the Sun, so temperatures should be reasonable, though probably somewhat warmer on average than Earth. However, we haven't found any proof yet that life actually exists there, and there are many reasons to be cautious about getting too excited. One major reason for our uncertainty is that the planet is so incredibly far away, 1,400 light-years, that we don't have the technology to directly observe its surface or definitively determine whether it has an atmosphere suitable for life. Even our most powerful telescopes can only tell us so much about such distant planets. We can detect their size by measuring how much starlight they block when they pass in front of their star. We can estimate their mass and therefore their gravity by observing their gravitational effect on their star. And sometimes we can get hints about their atmosphere, but we can't see surface details or definitively prove the presence of life with our current technology. Asterisk. But scientists have developed another ingenious method to study distant planets, and this method is called spectroscopy, and it's revolutionizing our ability to study exoplanet atmospheres. Spectroscopy works on a beautifully simple principle. when light from a star passes through or around a planet's atmosphere. It interacts with whatever gases are present in that atmosphere, and those gases absorb light at very specific wavelengths, leaving dark lines in the light spectrum like a barcode. Different gases absorb light at different wavelengths, so by carefully analyzing the light that passes through a planet's atmosphere, we can determine what gases are present there and in what quantities. Scientists can study that light using instruments called spectrographs and figure out which gases are present in that planet's atmosphere, building up a chemical fingerprint of the world. If they were to find certain combinations of gases, particularly oxygen combined with methane, it could be a very strong sign that life exists there. Because on Earth, these gases are present in our atmosphere primarily because of biological processes, because of life itself. Oxygen in our atmosphere comes mainly from photosynthetic organisms like plants, algae, and which have been producing oxygen for billions of years through the process of photosynthesis, taking in carbon dioxide and water and producing oxygen as a waste product. Without life constantly replenishing it, oxygen would quickly react with rocks and other materials and disappear from the atmosphere within a few million years. Methane is produced by various living organisms, including bacteria, in wetlands, in the digestive systems of animals, and through the decomposition of organic matter. Like oxygen, methane doesn't last long in the atmosphere naturally, so finding both oxygen and methane together would be very hard to explain without invoking biology. Without assuming that life is constantly producing these gases, however, we must be careful, because spectroscopy has its limitations and challenges that we need to acknowledge. Asterisk, we need the planet to pass directly in front of its star, from our perspective, an event called a transit, for atmospheric spectroscopy to work best. Not all planets have orbits aligned this way from our viewpoint, and those that don't are much harder to study. Additionally, even if we detect certain gases that could be produced by life, we can't always be completely certain they're actually produced by life because some gases can be created by non-biological geological processes as well. Oxygen can be produced by the breakdown of water molecules by ultraviolet light from the star, though usually not in large quantities. Methane can be produced by volcanic activity and certain chemical reactions in the planet's interior. This is why scientists look for combinations of gases, multiple biosignatures together, that would be very unlikely to exist together in significant quantities unless life was present to continuously replenish them. The detection of a true biosignature, a clear sign of life, would require finding multiple lines of evidence, multiple gases that together paint a compelling picture that could only be explained by biological activity. Asterisk, now let's talk about another absolutely fascinating planetary system called TRAPPIST, which might be the most exciting discovery we've made so far in the search for life beyond Earth. This system was discovered in 2017, and the announcement of its discovery made headlines around the world because of its incredible implications for the search for extraterrestrial life. According to scientists who have studied it intensively, it's the most promising candidate we've found so far where life could potentially exist, perhaps on multiple worlds in the same system. TRAPPIST-1 is a star system approximately 40 light-years away from us in the constellation Aquarius, which is relatively close in astronomical terms, close enough that future generations might actually be able to send probes there to study it up close. This system has not just one potentially habitable planet, but 7 Earth-sized planets, all orbiting very close to a small, cool star. Of these 7 planets, 3 are located in the habitable zone where liquid water could exist, tripling our chances of finding life in this one system alone. Asterisk, the most interesting and visually stunning thing about the TRAPPIST-1 system is that all 7 planets are so incredibly close to each other that if you were standing on the surface of one planet, you could clearly see the other planets in the sky, appearing much larger than our moon appears to us. Just as we can look up and see our moon hanging in the sky, inhabitants of a TRAPPIST-1 planet would look up and see other worlds, other planets with surfaces and features you could make out with the naked eye. Imagine what the sky would look like from one of these TRAPPIST-1 planets. Instead of just one moon to marvel at, you might see 2 or 3 other worlds hanging in your sky at any given time. Some appearing larger than our moon appears to us from Earth, glowing softly with reflected light from the star. During certain times in the orbital dance, you might witness spectacular eclipses where one planet passes in front of another, or see another planet pass in front of the sun, its silhouette visible against the star's disk. Asterisk, the gravitational interactions between these closely packed planets would create complex tidal forces much stronger than what we experience from our moon, potentially leading to fascinating and intense geological activity, including volcanism and earthquakes. If life somehow evolved independently on multiple planets in this system, and that's an exciting possibility that scientists are considering. There's even a theoretical possibility that life could have spread from one planet to another through a process called panspermia, where asteroid impacts blast material from one planet into space, and some of that material, possibly containing hardy microorganisms, eventually lands on another planet. seeding it with life. This means that all life in the TRAPPIST-1 system could potentially share a common origin, making them all cousins in a cosmic sense. Asterisk, the TRAPPIST-1 system is particularly interesting and unique because the star at its center is what we call an ultracool red dwarf, much smaller, cooler, and dimmer than our Sun. In fact, TRAPPIST-1 is barely larger than the planet Jupiter, though it's still massive enough to sustain nuclear fusion in its core, which is what makes it a star rather than a planet, because this star is so cool and dim, emitting only about 1/10% of the energy our Sun emits. The habitable zone is located much closer to the star than it is in our solar system. This is why all 7 planets orbit so tightly packed together in a space smaller than the orbit of Mercury. Our solar system's innermost planet, the innermost planet in the TRAPPIST-1 system, completes one full orbit in just 1.5 Earth days, whipping around the star at tremendous speed, while even the outermost planet only takes about 20 days to complete its orbit, still much faster than any planet in our solar system. Asterisk, because these planets orbit so close to their star, they're almost certainly tidally locked, which means the same side of each planet always faces the star, just like the same side of our moon always faces Earth. We never see the far side of the moon from Earth because it's tidally locked, and the same thing would be true for these planets. This tidal locking would create extreme and fascinating conditions, quite unlike anything we experience on Earth. One side of each planet would be in eternal daylight, constantly bathed in the dim red light of the star, baking under continuous radiation. The other side would be in eternal darkness, never seeing the star, freezing in perpetual night. Between these two extremes would be a narrow twilight zone, a band around the planet where the star would appear to hang forever on the horizon, neither rising nor setting, and conditions in this twilight zone might be more favorable for life than either the day side or the night side. Asterisk, life on such a tidally locked planet, if it exists, would face unique challenges and might evolve in ways we can barely imagine. On the day side, organisms would need to cope with constant radiation and heat, perhaps living underground or in caves during the hottest periods, or developing reflective surfaces or other adaptations to deal with the endless day. On the night side, life would need to survive in permanent darkness and extreme cold, perhaps clustered around volcanic vents that provide heat and energy, living in a way similar to the deep-sea vent communities on Earth that survive without any sunlight at all. The most habitable region would likely be the twilight zone, where temperatures are more moderate and where organisms could potentially migrate to follow their preferred conditions. Some scientists have even speculated that on such a world, you might have entirely separate ecosystems that never interact. Life forms on the day side that have never encountered life forms from the night side, evolving independently in their separate environmental niches. Asterisk. Now imagine if there really is life on these TRAPPIST-1 planets. What would it actually look like? And would there be tall, blue, Na'vi-like aliens as shown in the Avatar movie, with complex societies and advanced technology? Scientists are quick to point out that alien life could be completely, fundamentally different from anything we've ever seen or imagined. Life on Earth is carbon-based, meaning that carbon is the main element forming the backbone of our biochemistry, the foundation of all our proteins, DNA, fats, and carbohydrates. Carbon is ideally suited for this role because it can form strong bonds with many other elements and can create long chains and complex molecules, the intricate structures necessary for living organisms. But on another planet with different conditions, different temperatures, different chemistry, life might be based on completely different biochemistry. It could be silicon-based, using silicon instead of carbon as its fundamental building block. Or it could be based on some other element entirely that we haven't even considered, using chemistry that would seem bizarre and alien to us. Silicon sits right below carbon on the periodic table of elements, which means it shares some similar properties and chemical behaviors. Silicon can also form bonds with other elements and create chains, though not as easily or flexibly as carbon. This means silicon-based life is theoretically possible, though it would likely be very different from carbon-based life and might work better in very different environmental conditions. However, silicon-based biochemistry has significant limitations that make it seem less likely than carbon-based life. Silicon-oxygen bonds are much stronger and more stable than carbon-oxygen bonds, which means silicon-based life would have difficulty with the kind of dynamic, flexible biochemistry that carbon-based life enjoys. Life requires constant chemical reactions, constant building and breaking of molecules, and silicons, stronger bonds might make this too difficult. However, in environments very different from Earth, such as extremely cold worlds where chemical reactions naturally proceed more slowly, or planets with different atmospheric compositions where silicon chemistry might work better, silicon or other exotic chemistries might actually work better than carbon, giving rise to forms of life that would seem completely alien to us. Asterisk. Another thing scientists frequently mention is that if a planet's environment is very different from Earth, radically different in its gravity, temperature, atmospheric composition, or the type of star it orbits, then the life there will also be very different, adapted to those specific conditions in ways we might not immediately recognize as life at all. For instance, suppose there's a planet where gravity is 5 times stronger than Earth's gravity, where everything weighs 5 times what it would weigh here. The animals and plants there would need to be much shorter, more compact, and more robust because they would need to support much more weight under that crushing gravity. Trees might grow as wide bushes rather than tall trunks, unable to support their own weight if they grew too tall. Animals would probably be low to the ground, with thick, powerful limbs and incredibly strong bones and muscles, built like living tanks to handle the gravitational stress. Even simple activities like moving or eating would require adaptations we don't see on Earth. Asterisk, on the other hand, if there's a planet with very low gravity, perhaps a small world or a moon with only a fraction of Earth's gravitational pull, the creatures there could be tall, slender, and delicate, able to build towering structures and leap great distances with minimal effort. Flying would be much easier in low gravity, so you might see a much greater diversity of flying creatures. Perhaps even large flying animals that could never exist on Earth because our gravity would crush them. Plants might grow incredibly tall, reaching for the sky without needing thick, strong trunks because there's less gravity pulling them down. The entire ecosystem would be shaped by this fundamental physical difference. Asterisk, similarly, if a planet's star is red, meaning it's a cooler star that emits mostly red and infrared light rather than the full spectrum of visible light we get from our yellow sun, the plants there might also be red, purple, or even black rather than the green we're used to on Earth. On Earth, plants are green because chlorophyll, the molecule they use for photosynthesis, reflects green light while absorbing red and blue light. This makes perfect sense under our sun, which emits light across the full spectrum. But under a red dwarf star that emits mostly red and infrared light, plants would need to evolve different photosynthetic molecules that can efficiently capture that red light. They might be black to absorb as much of the limited light as possible, or they might be red or purple, reflecting the abundant red light they don't need while absorbing other wavelengths. The entire ecosystem would be adapted to the available light spectrum, creating a world that looks nothing like Earth. Animals might have different eye structures to see in the predominant wavelengths, perhaps seeing well into the infrared spectrum that would be invisible to human eyes. The whole web of life would be fundamentally different based on the energy source available from the star. Asterisk, now let's talk about some of Pandora's most spectacular and memorable special features from the Avatar movie, particularly those floating mountains that captured everyone's imagination. Could something like floating mountains really be possible anywhere in the universe, or is this purely fantasy? In the movie, it was explained that Pandora had a special mineral called unobtainium, and yes, that was actually the name they used in the film, and this miraculous mineral had the extraordinary property that it could float in a magnetic field, creating a natural levitation effect. The floating mountains contained massive deposits of this mineral, and Pandora's strong magnetic field provided the repulsive force that kept these mountains suspended in the air, creating one of the most visually stunning landscapes ever depicted in cinema. In real life, unfortunately, we haven't found any mineral or material that behaves quite like unobtainium, nothing that can float naturally in a planetary magnetic field. Asterisk, however, scientists have discovered and developed materials with some related properties that show this isn't entirely impossible, just extremely difficult. These materials are called superconductors, and they exhibit some truly fascinating properties that seem almost magical when you first encounter them. A superconductor is a material that, when cooled to very cold temperatures near absolute zero, loses all electrical resistance and can conduct electricity perfectly without any energy loss. Even more remarkably, superconductors exhibit a property called the Meissner effect, where they actively expel magnetic fields from their interior. This means that if you place a superconductor in a magnetic field and cool it below its critical temperature, it will actually repel that magnetic field and can float or levitate above a magnet, hovering in midair as if by magic. Scientists have demonstrated this effect in laboratories around the world, creating spectacular demonstrations where superconducting materials float above magnetic tracks, spinning and hovering without any visible support. Asterisk, however, and this is a crucial limitation, achieving superconductivity requires extremely cold temperatures, typically close to absolute zero at -273 degrees Celsius or -459 degrees Fahrenheit. Temperatures far colder than anything that occurs naturally on any planet's surface, except perhaps in the depths of space. Some superconductors work at slightly higher temperatures, and scientists are constantly searching for room temperature superconductors that would revolutionize technology. But even the warmest superconductors discovered so far require temperatures far colder than what you'd find on any habitable planet. So floating mountains made of superconducting materials would be essentially impossible on a world like Pandora, where the Na'vi can walk around breathing the air. Asterisk. The floating mountains in Avatar were one of the most visually stunning elements of Pandora, creating a landscape unlike anything else in cinema. but the physics behind making them work is quite complex and probably impossible. For mountains to float using magnetic levitation, they would need to contain absolutely massive amounts of magnetic or superconducting material. Tons and tons of it, and the planet would need to have an incredibly powerful magnetic field. Far stronger than anything we've observed on any planet. Earth's magnetic field is strong enough to protect us from harmful solar radiation and cosmic rays. And it's strong enough to make compass needles point north. But it's nowhere near strong enough to levitate mountains, or even small rocks. A magnetic field powerful enough to float entire mountains might be so extremely strong that it would interfere with normal biological processes, disrupting the electrical signals in nerves and brains, and might make the development of complex life very difficult or impossible. The energy required to maintain such a field would be enormous, and we don't know of any natural process that could sustain it. However, there are some exotic and speculative scenarios where something resembling floating islands or aerial ecosystems might be possible under very different conditions than what we see on Earth, on a planet with very low gravity, perhaps a small moon or world with only a fraction of Earth's mass, and with a very dense atmosphere, much thicker than Earth's atmosphere. Large structures or even living organisms might be able to float like balloons or blimps, held aloft by buoyancy in the thick atmosphere rather than by magnetism. If there were organisms or geological formations that contain gases lighter than the surrounding air, they could theoretically float at certain altitudes where the density of the air matches their average density. Some scientists have speculated about the possibility of floating balloon-like ecosystems in the upper atmospheres of gas giant planets like Jupiter or Saturn, where the pressure and temperature conditions at certain altitudes might allow for liquid water droplets suspended in the clouds, and potentially even microbial life drifting through the atmosphere, living and reproducing while floating perpetually through the clouds. Asterisk. Now let's discuss Pandora's incredible glowing forests, those bioluminescent jungles that emitted brilliant blue light at night, creating some of the most memorable and beautiful scenes in the film. Is something like this really possible on another world, or is this also pure fantasy? Actually, this is one aspect of Pandora that's very scientifically plausible, because even here on Earth, we already have many organisms that glow in the dark through a process called and it's more common than most people realize. In the ocean, which covers most of our planet, there are vast numbers of animals that glow in the dark, creating spectacular displays of living light. Jellyfish drift through the water, glowing with ethereal blue or green light. Certain species of fish have glowing lures, or spots that they use to attract prey or mates. And some squid can produce elaborate light displays across their bodies. Even some bacteria glow when they reach certain population densities, using light as a form of chemical communication in a process called quorum sensing. Asterisk. On land, the most famous example is the firefly, which lights up summer evenings with flashing yellow-green lights as part of their mating rituals. Even in forests, there are some species of mushrooms and fungi that glow at night with a soft, greenish luminescence, creating fairy tale-like scenes in dark woods around the world. This bioluminescence isn't just a curiosity or accident. It serves important functions for the organisms that produce it. Deep-sea creatures live in a world of perpetual darkness where sunlight never penetrates. And in that dark environment, bioluminescence becomes incredibly useful. Some creatures use their light to attract prey, dangling glowing lures to draw in curious fish or other animals. Others use bioluminescence to communicate with potential mates, creating specific patterns of flashes that signal their species and readiness to reproduce. Some organisms use bioluminescence to confuse or startle predators, suddenly flashing bright lights or ejecting glowing clouds to create a distraction while they escape. Asterisk. So, if there's a planet where life exists and the nights are very long, perhaps because the planet rotates slowly and each day-night cycle lasts for many Earth days or even weeks, or where the nights are very dark because the star is dim or the planet has a thick atmosphere that blocks light, the life there might very well evolve to be bioluminescent on a scale we've never seen on Earth. Entire forests could glow with their own light. Not just a few scattered organisms, but the majority of plants and animals, creating landscapes of living light. Plants might use bioluminescence to attract pollinators or seed dispersers during the long dark nights, glowing with colors and patterns that advertise their flowers or fruits to the creatures that can help them reproduce. Some plants might glow continuously, while others might flash in rhythmic patterns, creating a pulsing, breathing landscape of light. Animals might communicate using complex patterns of light across their bodies, flashing elaborate messages to each other like biological text messages, creating a visual language far more sophisticated than anything we see on Earth. Predators might use glowing lures or patterns to attract and confuse prey, while prey animals might use sudden bright flashes to startle predators, or synchronize flashing to confuse attackers about which individual to target. Asterisk. Imagine walking through such a forest at night. something the characters in Avatar experienced in those breathtaking scenes. Every step you take might cause the ground to light up beneath your feet as bioluminescent organisms react to the pressure and disturbance, creating a trail of light behind you like footprints made of stars. The moss and small plants covering the forest floor might glow softly in blues and greens, while larger plants pulse with deeper colors. Trees might pulse with waves of light traveling up and down their trunks, perhaps as they communicate with each other through underground fungal networks, sending signals about water availability, nutrient levels, or approaching threats. The light might travel from tree to tree, creating waves of illumination sweeping through the forest like the coordinated flashing of fireflies but on a massive scale. Flying creatures might leave glowing trails through the air as they move, like biological fireworks painting streaks of light across the darkness. These could be pollen or spores that glow as they're released, or perhaps mucus trails that bioluminesce, or even the creatures themselves glowing and leaving afterimages as they dart between the glowing trees. The entire ecosystem might be orchestrated in a symphony of light, with different species flashing in coordinated patterns that have evolved over millions of years. Perhaps certain times of night would see different displays, as different species become active at different hours, each with their own signature patterns and colors. During mating seasons, the displays might become even more elaborate and intense, as organisms compete for attention and try to attract the best mates with the most impressive light shows. The colors of bioluminescence we see on Earth are mostly blues and greens, because these colors travel well through water and are energetically efficient to produce. But on another planet with a different atmospheric composition, different wavelengths of light might travel better, and evolution might favor different colors. You might see reds, purples, ultraviolets, or even colors in spectra that human eyes can't detect at all, visible only to the alien organisms that evolved to see them. The chemistry of bioluminescence involves special proteins called luciferases that catalyze reactions producing light. And on another world, completely different chemical pathways might evolve to produce light, perhaps with greater efficiency or different properties than anything we see on Earth. It would truly be an alien and beautiful sight, yet completely possible and plausible based on biological principles we already observe right here on Earth. In fact, some scientists think that bioluminescence might actually be very common on planets orbiting red dwarf stars, which are the most numerous type of star in the galaxy. Red dwarfs are dim compared to our Sun, and planets in their habitable zones would receive much less light than Earth does. In such low light conditions, bioluminescence might become the dominant form of illumination during night periods, much more common and elaborate than what we see on Earth. The evolution of bioluminescence might be almost inevitable on such worlds, because organisms that can produce their own light would have such a tremendous advantage in navigation, communication, and finding food or mates. The most interesting thing to consider is that even if we grant all of these possibilities, even if we assume there's a planet like Pandora, somewhere out there in the cosmos with bioluminescent forests and exotic life forms, we still face an enormous practical problem. How would we even get there, to see it with our own eyes? As I told you earlier, even the nearest star system, Alpha Centauri, is over 4 light-years away, and with our current fastest spacecraft, the ones using the most advanced propulsion technology we've developed, it would take approximately 70,000 years to get there. That's an almost incomprehensible amount of time, longer than all of human civilization, longer than our species has been anatomically modern. Clearly, if we're ever going to explore distant star systems and search for life beyond Earth in person, rather than just through telescopes, we need something dramatically better than our current technology. But scientists and engineers are working on new revolutionary technologies that could potentially solve this seemingly impossible problem and make interstellar travel feasible within human lifetimes. One of the most promising and exciting technologies currently being developed is called breakthroughs, and this ambitious project involves creating tiny spacecraft, each about the size of a postage stamp or a computer chip, weighing just a few grams. These miniature spacecraft, called would carry ultra-miniaturized cameras, navigation equipment, communication devices, and scientific instruments, all compressed into an incredibly small package using the most advanced microelectronics we can develop. Each starship would be attached to an ultra-thin light sail, a reflective sheet just atoms thick, and these sails would be pushed through space using incredibly powerful laser beams fired from Earth. The concept works like this. Imagine an array of powerful lasers on Earth, perhaps built in the high, dry deserts of Chile or in space itself, working together to create a focused beam of light with millions of watts of power. This beam would be aimed at the light sail attached to the starship as it launches from Earth. Photons of light, despite having no mass, carry momentum, and when billions and billions of photons strike the reflective sail, they transfer their momentum, giving the spacecraft a tiny push. Individually, each photon provides only the tiniest amount of force, but with millions of watts of laser power hitting the sail continuously, the accumulated force becomes significant. Over just a few minutes of continuous acceleration, these tiny spacecraft could reach tremendous velocities that would seem impossible with conventional rocket propulsion. Asterisk, in this way, using pure light as propulsion, these Starship spacecraft could potentially reach 20 to 25% of the speed of light, about 60,000 kilometers per second. At these incredible velocities, much faster than anything humanity has ever built before. They could reach Alpha Centauri in approximately 20 to 25 years rather than 70,000 years. That's still a long time by human standards. Long enough that the scientists who launched the mission might be retired or deceased by the time the data comes back. But it's short enough to be achievable within a single human generation. A student working on the project in their 20s might be a senior scientist in their 50s when the first images and data arrive back from another star system. Asterisk, however, and this is important to understand, Breakthrough Starshot is still just an ambitious idea, a concept that faces enormous technical challenges. Actually building and deploying such a system would require solving numerous incredibly difficult engineering problems that we don't currently have answers for. The lasers would need to be extraordinarily powerful, far beyond anything we've ever built, requiring gigawatts of power and the ability to focus that power precisely over enormous distances. The light sails would need to be perfectly engineered to withstand the intense laser light without burning up, melting, or being damaged, while remaining incredibly thin and lightweight. They would need to be made of materials with exactly the right reflective properties. Materials we're still developing and testing. Asterisk, the tiny spacecraft would need to survive the journey through interstellar space, a hostile environment filled with cosmic radiation, micrometeorites, and the cold of deep space. Even a collision with a tiny dust particle at 20% of light speed would release enormous energy, potentially destroying the spacecraft instantly. The particle would hit with the force of an explosion, and at these speeds, even individual atoms and molecules in the sparse interstellar medium become like radiation. The spacecraft would need incredible shielding, despite its tiny size, and we don't yet know if that's even possible. Additionally, the spacecraft would need to be able to communicate back to Earth across light years of distance using incredibly weak signals, and our receiving stations on Earth would need to be sensitive enough to detect those faint whispers from the stars. Asterisk, even if we successfully sent such probes to Alpha Centauri. Solving all these technical challenges, there's another significant problem we need to consider: communication and data transmission. At 20% of light speed, it would take approximately 20 to 25 years for the spacecraft to reach the Alpha Centauri system and begin taking pictures and making measurements. But then the radio signals, carrying all that precious data, would need to travel back to Earth, and radio waves, like all electromagnetic radiation, travel at the speed of light. Since Alpha Centauri is 4.37 light-years away, it would take another 4.37 years for any signal to reach Earth. This means we wouldn't receive any data, not a single image or measurement, until almost 25 to 30 years after launch. An entire generation would pass between launch and receiving the first results. Asterisk, furthermore, the amount of data that could be transmitted by such a tiny spacecraft would be severely limited by the weak power available for the transmitter and the enormous distance the signal must travel. We might get a few pictures, some basic measurements of temperature, atmospheric composition, and magnetic fields, but nothing like the detailed high-resolution exploration we might hope for. There would be no way to steer the spacecraft or adjust its trajectory once it's been accelerated. No way to slow it down when it reaches its destination. It would simply fly through the Alpha Centauri system at tremendous speed, taking whatever pictures and measurements it can during the brief hours or days it spends passing through, and then continue flying off into deep space forever. Its mission complete. Despite these limitations, even a few images from another star system, even basic measurements of planets orbiting another sun, would be worth the effort and would revolutionize our understanding of the universe. Asterisk, another technology that people frequently talk about, especially in science fiction, is wormholes, and this concept captures the imagination like few other ideas in physics. A wormhole is a theoretical concept, a solution to Einstein's equations of general relativity, where there's a shortcut through the fabric of space-time itself. A tunnel connecting to distant points in space. Imagine you draw 2 points on a piece of paper, one at the top of the page and one at the bottom, and they're far apart if you measure the distance across the flat surface of the paper. But if you fold that paper so the 2 points touch, bringing them together, they're suddenly right next to each other, even though they haven't moved on the surface of the paper. You've created a shortcut by moving through the third dimension rather than traveling across the two-dimensional surface. Asterisk, similarly, according to the mathematics of general relativity, if space-time itself could be folded or curved in just the right way, creating what physicists call a wormhole or Einstein-Rosen bridge, we could potentially travel between two very distant points in space by passing through this tunnel. this shortcut through a higher dimension. Instead of traveling the long way around through normal space, covering all those light years at enormous cost in time and energy, you could step into one end of the wormhole and emerge almost instantly from the other end, potentially light years away. This would make interstellar travel essentially instantaneous, allowing us to reach distant stars and galaxies as easily as walking through a door. But here's the harsh reality that science fiction often glosses over. This is purely theoretical speculation at this point. Advanced mathematical concepts that might or might not reflect physical reality. The concept of wormholes comes from Einstein's theory of general relativity, the mathematical framework that describes gravity as the curvature of spacetime rather than as a force. The equations of general relativity are incredibly complex and allow for many different solutions. Many different ways that spacetime can be curved and structured. Wormholes are one of these mathematical solutions. They're allowed by the equations. But just because something is mathematically possible doesn't mean it actually exists in nature. We've never observed a wormhole, never detected any evidence that they exist anywhere in the universe. They remain purely theoretical constructs, ideas on paper that might or might not have any connection to reality. Even if wormholes do exist naturally somewhere in the universe, and that's a huge if, they would likely be incredibly unstable and would collapse immediately. Closing off the shortcut almost as soon as it forms, the mathematics suggests that wormholes would need to be held open by some form of exotic matter with negative mass or negative energy density, something that would push spacetime apart rather than pulling it together like normal matter does. This is called exotic matter, and it's completely hypothetical. We've never observed anything like it, never detected it, never created it in a laboratory. We don't even know if it's physically possible for such matter to exist, or if it's merely a mathematical curiosity that the equations allow but nature forbids. Third, even if we could somehow find or create a stable wormhole held open by exotic matter, the tidal forces near its entrance and exit might be so enormously strong that any object trying to pass through would be torn apart at the atomic level, stretched and compressed by gravitational forces billions of times stronger than anything we could survive. You might be stretched into a long, thin strand of atoms in one direction while being compressed in the other directions, a process physicists whimsically call spaghettification. Only the very largest wormhole, if they exist, might have gentle enough tidal forces near their mouths to allow passage, and creating or finding such a wormhole would require technology far beyond anything we can currently imagine. Science fiction has given us wonderful, captivating images of spacecraft jumping through wormholes to travel across the galaxy in moments, visiting distant civilizations and exploring strange new worlds. But the reality is that this technology remains pure speculation, wishful thinking based on mathematical possibilities. Most physicists believe that even if wormholes do exist somewhere in the universe, and that's far from certain, they're probably microscopic, smaller than atoms, lasting for only infinitesimally small fractions of a second before collapsing, and could never be used for space travel in any practical sense. They would wink in and out of existence at the quantum level, too small and too brief to be useful. However, some theoretical physicists continue to study these possibilities seriously, not because they think wormhole travel will be possible anytime soon, but because understanding these extreme solutions to Einstein's equations might teach us something fundamental about the nature of spacetime, gravity, and the universe. They're looking for ways that the laws of physics might permit such shortcuts through spacetime under very special conditions, and whether there might be any practical way to create, stabilize, or utilize them. Even if wormholes never become a means of transportation, studying them advances our understanding of physics and might lead to unexpected breakthroughs in other areas. Now, there's a very important and fascinating question that many people ask. A question that goes to the heart of the search for extraterrestrial intelligence. If the universe is so vast, if there are so many stars and planets, so many places where life could exist, so much time for life to evolve and civilizations to arise, why haven't we found aliens yet? Why haven't they found us? Where is everybody? Scientists call this profound puzzle the Fermi paradox, named after Enrico Fermi, a famous physicist who first posed this question clearly during a lunch conversation in 1950. His colleagues were discussing the possibility of alien civilizations in interstellar travel, and Fermi suddenly asked, "But where is everybody?" His point was simple but devastating. If aliens are common, some of them should have visited Earth by now, or at least made their presence obvious to us. So where are they? This question has haunted scientists and philosophers for over 70 years now. And despite decades of serious thought and research, there's still no definitive, universally accepted answer. The paradox is very real and very puzzling. Our galaxy alone contains hundreds of billions of stars, and we now know that most of those stars have planets orbiting them. The galaxy is approximately 13 billion years old, much older than our solar system, which formed only about 4.5 billion years ago. Even if intelligent, technological civilizations are quite rare. Arising on only 1 in a million suitable planets, there should still be thousands of such civilizations in our galaxy alone. If even a tiny fraction of those civilizations developed space travel and began expanding beyond their homeworlds, colonizing other star systems and spreading throughout the galaxy, they should have had plenty of time to colonize the entire galaxy many times over. The numbers simply don't add up. Asterisk, some scientists propose what's called the zoo hypothesis, the idea that alien civilizations know about us but are deliberately avoiding contact, perhaps observing us from a distance like we might observe animals in a zoo or a nature preserve. Maybe they have some kind of ethical code, a cosmic version of Star Trek's Prime Directive, that prohibits them from interfering with less advanced civilizations. They might be waiting for us to reach a certain level of technological or social development before making contact, watching to see if we'll destroy ourselves or mature into a species worthy of joining some galactic community. Or perhaps they're conducting a long-term scientific study of our development, and contacting us would contaminate their experiment. This hypothesis is possible but raises its own questions. Why would all alien civilizations follow the same non-interference policy? Wouldn't at least one of them break the rules? Asterisk, others suggest what's called the Great Filter Hypothesis, and this is one of the more sobering possible answers to the Fermi paradox. This idea proposes that there's some incredibly difficult step or obstacle in the evolution of intelligent life. Some filter that very few species successfully pass through. Either we've already passed this filter, which is why we exist at all, and why we don't see anyone else, because they never made it this far, or the filter is still ahead of us in our future, which might be very bad news for humanity's long-term survival. Maybe the filter is the origin of life itself. And life is so incredibly rare that Earth might be the only living planet in our entire galaxy. Or maybe the filter is the development of complex multicellular life, or the evolution of intelligence, or the development of technology. Or, more ominously, maybe the filter is ahead of us. Perhaps all civilizations destroy themselves shortly after developing advanced technology, through nuclear war, environmental catastrophe, artificial intelligence gone wrong, or some other existential threat we haven't even imagined yet. Asterisk, some scientists say that perhaps aliens have hidden themselves because there's some danger in the universe that we don't know about. Some threat that makes advertising your presence extremely dangerous. Maybe broadcasting your existence to the cosmos is cosmically foolish. And all wise civilizations quickly learn to hide and stay quiet. This idea, sometimes called the dark forest hypothesis after a science fiction novel that popularized it, suggests that the universe might be like a dark forest where predators lurk in the shadows. Every civilization is a hunter creeping quietly through this forest, and survival depends on staying silent and hidden. Any civilization that makes noise, that announces its presence, might be destroyed by predators, by hostile aliens with superior technology who eliminate potential competitors or threats. If this dark scenario is true, then our radio and television broadcasts over the past century, signals that have been radiating out into space, announcing Earth's presence and location, might have been incredibly foolish and dangerous, potentially attracting unwanted and hostile attention from aggressive civilizations. Asterisk, some scientists believe that maybe we really are alone, or at least that intelligent life is so incredibly rare that there's no one else in our cosmic neighborhood, no other civilizations within thousands of light years. This is called the rare Earth hypothesis, and it suggests that while simple microbial life might be relatively common in the universe, arising wherever conditions are right, complex multicellular life and especially intelligent, technological life might be extraordinarily rare, perhaps unique to Earth. This hypothesis points out that Earth had to have so many things go exactly right for intelligent life to evolve here. We needed the right size star that would burn steadily for billions of years, the right distance from that star to maintain liquid water, a large moon to stabilize our axial tilt and create tides, Jupiter to act as a gravitational shield protecting us from asteroid impacts, plate tectonics to recycle nutrients and regulate our climate, a magnetic field to protect us from deadly radiation, and countless other factors that all had to align perfectly. Asterisk, maybe the combination of all these factors happening together on one world is so incredibly rare, such an unlikely cosmic coincidence, that we might be the only intelligent life in our entire galaxy, or even in the observable universe. If this is true, it makes Earth and humanity precious beyond measure, the universe's only way of understanding itself, and it places an enormous responsibility on us to preserve our world and ourselves. The extinction of humanity would be not just a human tragedy but a cosmic one, silencing the only voice the universe has ever produced. Asterisk, but in my opinion, based on what we know about the universe, the most logical explanation for the Fermi paradox is much simpler and less dramatic than these exotic scenarios. The universe is so absolutely enormous and our technology is still so limited and primitive. that we've only just barely begun searching for other civilizations. We've searched only a tiny, infinitesimal fraction of the places where life might exist. We've discovered only a few thousand exoplanets so far out of the hundreds of billions that exist in our galaxy alone. We've listened for radio signals from only a few thousand nearby stars out of hundreds of billions. We've been seriously searching for extraterrestrial intelligence for only about 60 years, which is an eye blink in cosmic time, less than 1/billionth of the age of the galaxy. Consider this sobering fact. We've been broadcasting radio signals into space for only about 100 years. Since the early days of radio in the 1920s, those signals have only traveled about 100 light-years from Earth, forming a bubble of radio noise expanding outward at the speed of light. In a galaxy that's 100,000 light-years across, that 100-light-year bubble is like whispering in one tiny corner of a massive stadium and wondering why nobody across the field has heard you yet. We've barely made any noise at all on a cosmic scale. Furthermore, our radio signals degrade with distance, spreading out and weakening as they travel. And beyond a certain distance, they become indistinguishable from background noise, lost in the cosmic static. An alien civilization would need very sensitive radio telescopes, pointed exactly at our solar system at exactly the right time, and tuned to exactly the right frequencies to detect our presence. The same is true in reverse. We could only detect their signals if everything lines up perfectly. Asterisk, we've examined closely only a tiny handful of star systems, and our radio telescopes can only detect signals if they're pointed in exactly the right direction at exactly the right time, and if the aliens are using radio frequencies similar to what we use. If aliens use some completely different communication technology, something more advanced than radio that we haven't even invented yet, we wouldn't detect them at all. They could be broadcasting all around us and we'd be completely oblivious. Like someone using a telegraph trying to detect Wi-Fi signals. The absence of evidence is not evidence of absence, especially when we've barely begun to look. Asterisk now, let's talk about what would actually happen if we did find aliens someday. If we detected a signal from space or received a visit from an extraterrestrial civilization. This is a question that scientists, philosophers, and science fiction writers have pondered extensively. Many scientists say that if aliens are significantly more advanced than us, possessing superior technology and capabilities, it could potentially be very dangerous for us. And history provides some sobering lessons about what happens when civilizations with different technology levels meet. Throughout history, whenever an advanced civilization encountered a less advanced civilization, things usually went very badly for the less advanced one. The more advanced civilization, whether deliberately or accidentally, typically dominated, exploited, or destroyed the less advanced one. Asterisk, for example, when Europeans arrived in the Americas beginning in the 1490s, you know what happened to the native people there? Despite having lived in the Americas for thousands of years, developing their own sophisticated civilizations with impressive achievements in agriculture, architecture, astronomy, and art, the native populations were devastated by European contact. They had no immunity to European diseases, which killed millions. Their lands were taken, their cultures were suppressed or destroyed, their populations decimated by violence and exploitation. Within a few centuries, civilizations that had thrived for millennia were nearly wiped out. This happened not because Europeans were necessarily more evil than other people, but because they had technological advantages in weapons, transportation, and organization, and because they came from a culture that valued expansion and resource extraction. Above coexistence with indigenous peoples. Asterisk, if aliens arrive on Earth with technology far superior to ours, we might find ourselves in a similar position to those native peoples, essentially helpless against a force we cannot resist or even fully understand. They might view us as we view bacteria or insects, interesting to study, perhaps, but not worthy of moral consideration, easily destroyed if we become inconvenient. They might want Earth's resources, our water, our minerals, our biological diversity, or even our planet itself. And with superior technology, they could simply take what they want with little regard for our protests or survival. They might not even recognize us as intelligent beings worthy of consideration. If their intelligence is structured very differently from ours, if they think in ways we can't comprehend, they might not understand that we're conscious, thinking beings with rights and feelings. We might seem as simple and insignificant to them as ants seem to us. And most people don't hesitate to destroy an anthill if it's in the way of a construction project. Asterisk, some scientists worry that even well-intentioned contact could be catastrophic for humanity. Advanced aliens might share their technology with us out of generosity or curiosity, but that technology might be so far beyond our understanding that it would destabilize our societies. Imagine if you gave modern weapons, computers, and machinery to a civilization from the Bronze Age. The sudden influx of incomprehensible technology would likely cause massive social upheaval, destroying existing power structures and economic systems, potentially leading to wars and chaos as different groups fought to control or understand the new technology. Similarly, alien technology or knowledge might be so advanced that it would render our own achievements meaningless, destroying human initiative and purpose. Why would we bother doing science or exploring if aliens can simply give us all the answers? The psychological and social impact could be devastating even if the aliens mean us no harm. Asterisk, however, and this is an important counterpoint. Some scientists argue from a more optimistic perspective that any civilization advanced enough to travel between stars would have necessarily developed. Beyond violent and destructive tendencies, they point out that a species that remains fundamentally warlike, aggressive, and short-sighted would likely destroy itself before ever developing interstellar travel capability. Think about humanity's current challenges. We have nuclear weapons capable of destroying our civilization. We're changing our climate in ways that could make our planet uninhabitable. We're developing artificial intelligence that might surpass and replace us. We're depleting our resources and destroying our ecosystems. These represent existential threats that a civilization must successfully navigate and overcome to survive long enough to reach for the stars. Asterisk, any alien civilization that has survived long enough to develop interstellar travel, surviving for thousands or millions of years without destroying themselves, would have had to solve all of these problems and more. They would have had to develop sustainable ways of living, ways of managing powerful technologies without annihilating themselves, systems of government and social organization that prevent self-destruction. This suggests that truly advanced civilizations might be peaceful by necessity, having learned through painful experience that violence and aggression lead only to extinction. They might approach other civilizations with curiosity and benevolence rather than hostility, seeing the value in diversity and cooperation rather than domination and exploitation. They might even have ethical or spiritual beliefs that emphasize the sanctity of all life and the importance of preserving developing civilizations. Asterisk, there's also the fascinating possibility that aliens might be so fundamentally different from us that traditional concepts of conflict or cooperation wouldn't even apply to our relationship. They might be silicon-based life forms that don't need the same resources we do, living in environments we find completely uninhabitable and having no interest in our water, oxygen, or organic compounds. They might exist in forms we can barely imagine or recognize as life, as clouds of nanobots working in perfect coordination, as patterns of energy propagating through magnetic fields, as collective consciousnesses spanning entire planets where billions of individual organisms function as a single thinking entity. They might exist on such different timescales that communication would be nearly impossible, thinking and acting so slowly or so quickly that we can't even recognize their actions as deliberate. Asterisk. Communication itself might be the greatest challenge, far more difficult than science fiction usually portrays. If their sensory organs, their ways of perceiving the universe, are completely different from ours, how would we even begin to establish a common language or system of communication? If they don't see, hear, touch, taste, or smell the way we do. If they perceive the universe through senses we don't possess and can't imagine, finding common ground might be extraordinarily difficult. They might communicate using modulated gravitational waves or quantum entanglement, or by releasing complex chemical signals, or through some mechanism we haven't even discovered yet. They might not even recognize us as intelligent beings if our intelligence manifests in ways they don't associate with consciousness. They might think in ways so alien to us that we share no common concepts, no common framework for understanding reality. Human thought is shaped by our evolutionary history, by millions of years of adaptation to life on Earth, by our specific sensory capabilities, by our social nature, by the particular challenges our ancestors faced. Alien thought might be shaped by completely different evolutionary pressures and might operate on completely different principles. What seems logical or obvious to us might be incomprehensible to them, and vice versa. Establishing any kind of meaningful communication or relationship might require generations of patient effort on both sides, gradually building up shared concepts and mutual understanding from the most basic common ground we can find. Asterisk, some scientists have proposed detailed protocols for what humanity should do if we detect an alien signal or make contact with an extraterrestrial civilization. The SETI Post-Detection Protocol, developed by scientists involved in the search for extraterrestrial intelligence, outlines careful steps that should be followed. First, any detection must be thoroughly verified to ensure it's genuinely from an alien intelligence and not a natural phenomenon, equipment malfunction, or human-made signal. History is full of false alarms where scientists thought they'd detected alien signals that turned out to be stars, or satellites, or even microwave ovens in the break room. Once a signal is verified as genuinely extraterrestrial and artificial, the information should be shared immediately with other scientists around the world for independent verification and analysis. The general public and news media should be informed as soon as possible, because this would be one of the most important discoveries in human history, something that concerns all of humanity rather than any one nation or group. Asterisk, then comes the really difficult question. Should we reply? Should we send a message back, attempting to establish communication, or should we remain silent, observing without revealing our presence? The reasoning behind considering silence is straightforward. If we detect a signal from aliens, it means they're at least as advanced as we are, and possibly much more advanced, capable of things we can't even imagine. We should be very careful and thoughtful about how we respond, if we respond at all. Some scientists, including the late Stephen Hawking, one of the most brilliant physicists of our time, warned strongly against trying to contact aliens at all. Hawking argued that we should listen, searching passively for signals, but we should not broadcast our presence or location. His reasoning was based on the historical precedent of what happens when more and less advanced civilizations meet, and on the recognition that we simply can't predict what alien intentions or capabilities might be. Asterisk. Hawking suggested that aliens advanced enough to receive and respond to our messages would likely be advanced enough to travel to Earth if they chose to, and we have no way of knowing whether they would come in peace or with hostile intent. Better, he argued, to remain quiet and hidden, observing the universe around us but not drawing attention to ourselves, at least until we're more advanced ourselves and better able to deal with whatever we might encounter. Other scientists disagree, arguing that any civilization capable of detecting our signals and traveling here would have detected our accidental radio and television broadcasts anyway, which have been leaking into space for a century. In their view, we've already announced our presence, so we might as well try to communicate deliberately and thoughtfully. Asterisk. The debate continues, with valid arguments on both sides, and humanity has not reached any consensus about how to handle potential contact. Different groups and nations might make different choices, and there's currently no international treaty or agreement governing how humanity should respond to alien contact. This lack of coordination could itself be problematic if contact occurs, with different groups potentially sending conflicting messages or taking actions that affect all of humanity, without global consent. Asterisk. Now let's talk about what we can learn from this entire discussion. From all of our exploration of these ideas about life beyond Earth, about the search for worlds like Pandora, about the possibility of alien intelligence and what it might mean for us, when we seriously study the universe, when we look at other planets and star systems and try to understand the conditions necessary for life, we realize one profoundly important thing. Our Earth is incredibly, almost unbelievably, special. We live on a world that appears to be extraordinarily rare, a cosmic oasis of life in a vast desert of barren rock and gas. Everything on Earth is not just good, not just adequate, but absolutely perfect for life as we know it, fine-tuned to an extraordinary degree that seems almost miraculous. When you examine it closely, asterisk, our sun is exactly the right size, not too large and not too small, burning steadily and predictably with only minor variations in output. Larger stars burn hotter and faster, exhausting their fuel in millions rather than billions of years. Not enough time for complex life to evolve. Smaller stars, while they last for trillions of years, are often unstable, producing dangerous flares and radiation that would sterilize any nearby planets. Our sun is in the sweet spot, providing steady, reliable energy for billions of years. We orbit our sun at exactly the right distance, not so close that our oceans boil away like Venus, not so far that everything freezes solid like Mars. This perfect distance puts us in the habitable zone where liquid water can exist year-round, where temperatures allow for the complex chemistry that life requires. Asterisk, we have a large moon, unusually large for a planet our size, and this moon has been crucial to the development of life on Earth in ways we're only beginning to fully understand. The moon's gravitational pull creates tides, rhythmic rising and falling of our oceans that may have been important for the origin of life, creating tidal pools where organic molecules could concentrate and interact. The moon also stabilizes Earth's axial tilt, keeping it relatively steady at about 23.5 degrees rather than wobbling chaotically. This stable tilt gives us stable, predictable seasons that have remained consistent for billions of years, allowing life to adapt to regular patterns rather than facing random, catastrophic climate swings. Without our moon, Earth's axis might wobble wildly, causing the climate to fluctuate between extreme states, making the evolution of complex life much more difficult or perhaps impossible. Asterisk, we have Jupiter, that massive gas giant orbiting in the outer solar system, and Jupiter acts as a gravitational shield, a cosmic protector for Earth. Jupiter's enormous mass, more than 300 times Earth's mass, creates a powerful gravitational field that attracts and captures many asteroids and comets that might otherwise strike Earth. Some of these objects still get through Jupiter's defenses, and the impacts that do occur have sometimes caused mass extinctions like the one that killed the dinosaurs 65 million years ago. But without Jupiter, such impacts would be far more frequent. perhaps so frequent that complex life could never gain a stable foothold. We might be bombarded constantly, with massive impacts every few million years instead of every few 100 million years, preventing any civilization from ever developing. Asterisk, we have a strong magnetic field, generated by the motion of molten iron in Earth's core, and this invisible shield protects us from the solar wind, the stream of charged particles constantly flowing from the sun. Without this magnetic field, the solar wind would gradually strip away our atmosphere, molecule by molecule, leaving Earth as barren as Mars, which lost most of its magnetic field billions of years ago, and subsequently lost most of its atmosphere. Our magnetic field deflects these particles, channeling them toward the poles where they create beautiful auroras, the northern and southern lights, rather than allowing them to erode our precious atmosphere. We have plate tectonics, the slow but constant movement of Earth's crust, with continents gradually drifting across the surface over millions of years. This might seem like a purely geological phenomenon with no connection to life, but plate tectonics is actually crucial for maintaining Earth's habitability over geological time. As plates move and collide, they recycle carbon dioxide from the atmosphere into the Earth's interior, preventing a runaway greenhouse effect that would make Earth uninhabitable like Venus. They also release carbon dioxide back into the atmosphere through volcanism, preventing Earth from freezing solid. This carbon cycle, driven by plate tectonics, acts like a thermostat, keeping Earth's temperature within a narrow range suitable for life for billions of years. Most planets probably don't have plate tectonics with their crusts locked in place, unable to recycle materials and regulate their climates. Asterisk, if any of these factors were even slightly different. If our sun were a bit larger or smaller, if Earth orbited a bit closer or farther away, if we had no moon or a smaller moon, if Jupiter didn't exist or orbited elsewhere, if we had no magnetic field, if we had no plate tectonics, then life on Earth, especially complex, multicellular life, and certainly intelligent life, might never have developed. We are the product of an extraordinary series of fortunate circumstances, cosmic coincidences that all happen to align in just the right way at just the right time. Understanding this should fill us with wonder and gratitude, and it should also make us realize how precious and fragile our world is, how careful we must be to preserve it. Asterisk, this brings us to the final question, the one we started with: does a place like Pandora really exist somewhere in the universe? What's the final answer after all this exploration and discussion? The truth is that we probably won't find a planet exactly like Pandora, precisely matching the fictional world created for the Avatar movie, because that was an imaginary place designed for cinematic storytelling rather than scientific accuracy. The floating mountains, while visually spectacular, probably can't exist as depicted. The particular ecosystem with its specific bioluminescent forests and its neural interface biology was created by artists and designers for dramatic effect. The 10-foot-tall blue aliens are products of imagination rather than evolutionary biology. Asterisk, but here's what we can say with confidence. Planets where life is possible, where conditions are right for biology to emerge and evolve and potentially create complex and wonderful forms. Those definitely could exist, probably do exist, scattered throughout our galaxy and the wider universe. We've already found thousands of exoplanets, and the more we look, the more we find. Many of these planets are in their stars' habitable zones, where liquid water could exist. Some of them are Earth-sized or close to it. Some orbit sun-like stars. With every new discovery, with every advance in our telescopes and detection methods, we find more potentially habitable worlds, more places where life might have gained a foothold. Asterisk, statistical probability strongly suggests that with hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies in the observable universe, life must have arisen elsewhere, probably many times, creating worlds with their own unique ecosystems, their own forms of life adapted to their particular conditions. Some of these worlds might be even more spectacular and beautiful than Pandora, with landscapes and life forms that would take our breath away if we could see them. Others might be subtle and strange, with life so different from what we know that we might not even recognize it at first glance. Asterisk, when our technology becomes more advanced, when we develop better telescopes that can directly image exoplanets rather than just detecting them indirectly, when we can analyze their atmospheres in detail looking for when we can perhaps send probes to nearby star systems, maybe we'll find these worlds. Maybe we'll see their alien forests and oceans with our own eyes, or at least through the cameras of our robots. Within this century, possibly within our lifetimes, we might detect clear evidence of life on another world, perhaps seeing oxygen and methane together in an exoplanet's atmosphere, or detecting radio signals from an alien civilization, or finding fossilized microbes on Mars or living organisms in the oceans of Europa or Enceladus. Asterisk, each of these discoveries would be revolutionary, changing forever how we see ourselves and our place in the cosmos. Finding even simple microbial life on another world would prove that life is not unique to Earth. that it arises naturally wherever conditions are right, suggesting that the universe might be teeming with life. Most of it microbial, but some of it perhaps complex and intelligent. Finding intelligent life, making contact with another civilization, would be even more profound, raising questions about the nature of intelligence and consciousness, about the paths that evolution can take, about what it means to be alive and aware in this vast universe. Asterisk, the search for life beyond Earth is more than just scientific curiosity, more than just an academic exercise. It's a fundamental quest to understand who we are, where we came from, and whether we're alone in the universe. Every human culture throughout history has looked up at the stars and wondered if anyone is looking back, if we have cosmic companions sharing this mysterious existence. For most of human history, we could only wonder and speculate, creating myths and stories to fill the void of our ignorance. But now, for the first time, we have the tools to actually find answers, to search systematically for life beyond Earth and perhaps find it. Asterisk, the implications of finding life, or of definitively proving that we're alone, would reshape human civilization in profound ways. If we find that life is common, that it arises on most suitable planets, then the universe suddenly becomes a much more interesting and hopeful place, full of diversity and possibility. We would know that we're part of a much larger story, participants in a cosmic drama that spans the universe. If we find that we're alone, or that life is so rare that we might be the only instance in billions of light years, then Earth and humanity become infinitely precious. The universe's only voice, its only way of understanding itself. Asterisk, either answer would be profound and transformative. Either answer would change how we see ourselves and our responsibility to our planet and our species. If we're alone, then we have a cosmic responsibility to preserve ourselves and our biosphere, because we might be the only life that exists, the only consciousness in a vast, dead universe. If we're not alone, then we're part of a larger community, and we need to think carefully about our place in that community, and how we want to present ourselves to our cosmic neighbors. Asterisk, as we continue our search, as we build better telescopes and send more probes and analyze more planets, we're writing the next chapter in humanity's story. The chapter where we finally answer the ancient question of whether we're alone. We're living through an extraordinary time in human history. The first generation with the tools to seriously search for life beyond Earth and potentially find it. Our grandchildren might grow up knowing for certain that life exists elsewhere, might study alien biochemistry in school, might communicate with alien civilizations, or they might grow up knowing we've searched thoroughly and found nothing, making Earth even more precious in their eyes. Asterisk. The journey to answer these profound questions will require global cooperation on an unprecedented scale, bringing together scientists, engineers, and visionaries from every nation and culture. It will require massive investments in science and technology, building telescopes more powerful than any we've conceived, developing spacecraft capable of reaching nearby stars, creating instruments sensitive enough to detect the faintest whispers of life in distant atmospheres. It will require patience and persistence, as the discoveries might take decades or even centuries to achieve. The scientists who begin this search might not live to see its conclusion, passing the torch to future generations who will continue the work. Asterisk, but the potential rewards make every bit of effort worthwhile. The knowledge that we share this universe with others, that life has emerged independently on multiple worlds, that intelligence and consciousness have arisen through different evolutionary paths under alien suns, would be worth any cost and any weight. Even the negative result, the growing certainty that we might be alone, would be valuable knowledge, sobering and profound in its own way, teaching us just how special and precious our little blue world really is. Asterisk, every child who looks up at the stars on a clear night and wonders if anyone out there is looking back at them. Every scientist who dedicates their career to this search despite the long odds and the possibility of never finding anything. Every engineer who designs the telescopes and spacecraft that extend our reach into the cosmos. Every person who supports this research and believes in its importance. They're all part of humanity's greatest adventure. This is the quest to understand our place in the cosmos, to find out if we have cosmic companions sharing this journey through space and time, to discover whether the universe is alive in ways we can barely imagine, or whether Earth is a singular miracle in an otherwise barren cosmos. The search for worlds like Pandora, for life beyond Earth in all its possible forms, is ultimately a search for ourselves, for our origins and our destiny. By studying other worlds, we better understand our own. By imagining alien life, we better appreciate the life around us. By reaching for the stars, we discover what makes us human. The questions we're asking about life in the universe are really questions about life itself, about what it means to be alive, to be conscious, to wonder and dream and search for meaning in a vast and mysterious universe. Asterisk, so now I want to know, what do you think after all of this exploration and discussion? Do you believe aliens exist somewhere out there in the cosmic ocean? And do you think we'll meet them one day, making contact with another civilization and joining a galactic community? Or do you think we're alone in this universe? The only island of life and consciousness in an infinite sea of stars and darkness. Do you think worlds like Pandora exist with bioluminescent forests and exotic ecosystems? Or is Earth unique in its beauty and diversity? What would you want to say to aliens if we made contact? What questions would you ask them? What would you want them to know about humanity and Earth? Asterisk, the answer to these questions will shape not just our scientific understanding of the universe, but our philosophy, our religions, our art and culture, our sense of purpose, and our vision for humanity's future among the stars. How we answer determines what kind of future we build, whether we see ourselves as cosmic orphans alone in the universe or as one civilization, among many in a populated cosmos. It determines whether we feel the weight of cosmic responsibility, as possibly the only consciousness the universe has produced, or the excitement of potential discovery and contact with alien minds. Asterisk, these are perhaps the most profound questions we can ask. Questions that touch on the deepest mysteries of existence. Why is there something rather than nothing? What is life, and how did it begin? What is consciousness, and how does it emerge from matter? Are we alone, or are we part of a larger community of living, thinking beings? The search for life beyond Earth, the search for worlds, like Pandora, is really a search for answers to these fundamental questions that have puzzled humanity since we first became aware of our own existence and our place in the vast cosmos surrounding us.